Okay, so now let's address the problem of computation. So what we've seen is that the definition of a determinant is recursive. And what this means is that the formula for an n by n determinant depends on the formulas for determinants of smaller matrices. And this poses a serious issue. Consider the issue of taking a determinant of a 10 by 10 matrix. Well, according to the formula, that 10 by 10 matrix has determinant with 10 different terms. Each one of those 10 terms involves the formula for a 9 by 9 determinant. And each one of those 10 9 by 9 determinants has 8 terms, and has 9 terms, and each one of those 9 terms involves the formula for an 8 by 8 determinant. And as we go down the ladder, we end up with hundreds and hundreds of determinants to take, and this gets out of hand very quickly. So we'd like to build some tools and strategies for help easing the burden of computation. And one major advancement here is what's called cofactor expansion theorem. So if we think about the original definition of the determinant we've been using, essentially what we've been doing is dropping down the first column, plucking out those entries, and multiplying by cofactors. What the cofactor expansion theorem says is we don't have to do this with only the first column. We can work with any column we want or any row we want to take our determinant. So rigorously, here's how to do it. Let's fix a value of I between 1 and n. For the ith column expansion, the value of I represents the column we will utilize. The cofactor expansion theorem says one way to calculate the determinant is to sum from k equals 1 to n, take the k-ith entry in the matrix, that's the kth entry in the ith column, and then scale by the ki cofactor. It turns out that when we add all of these terms up, we always produce the determinant of our matrix. The ith row expansion works much in the same way. Here, I represents the row we are going to expand about, and an alternative formula for the determinant says now we can sum from k equals 1 to n, where we pluck out the ik entry, so this is the kth entry in the ith row, and then we scale by the ik cofactor. This will also produce the determinant of our matrix. So the cofactor expansion theorem gives us freedom to calculate our determinant by choosing any row or any column to do our calculation over. So let's just see some examples where we write down the terms for the determinant by choosing a particular row or a particular column. So here we have a 3 by 3 determinant, and we're going to show what it looks like to use the second row to calculate the determinant about. So the second row of this matrix consists of the numbers 7, 0, and negative 66. So in our 3 terms for the determinant, we are going to have 7, and then we will scale by plus or minus 1, 0 scaled by plus minus 1, and negative 66 scaled by plus minus 1. Now, the way we choose our scaling of plus minus 1 is determined by the cofactor formula. 7 in this matrix is in the 2, 1 position, and negative 1 to the 2 plus 1 is negative 1 cubed, which is negative 1. So we start by scaling our value of 7 by negative 1. Once we determine the first scaling, everything else alternates in order. So now we are adding 0, and then we will subtract negative 66. So those are the scalars that we're using, but then once we pluck out these scalars, we want to multiply each one by the appropriate minor. For the first term, remember our 7 is in the 2, 1 position, so we should delete the second row in the first column and take a determinant of whatever's left over. Our 0 is in the second row, second column, so we should take 0 and multiply it by the determinant obtained by deleting the second row and second column of our original matrix. For the last term, we are subtracting negative 66, and then we multiply by the determinant obtained by deleting the second row, third column of our matrix. So now we have all 3 of our terms for the determinant of our 3 by 3, and each one of these 3 terms depends on the formula for a 2 by 2 determinant. So now if we took these 3 2 by 2s and added everything up, we would get the determinant of the original matrix. So this is a second row determinant expansion. Let's say we want to calculate the same determinant, but instead of using the second row expansion, we use the third column expansion. Now we're focused on the third column of this matrix, where the entries are -15, -66, -4. Well, according to the cofactor expansion theorem, we will now have 3 terms, but the scalars we're using are -15, -66, and -4. Now, we need to scale each one of these numbers by plus or minus 1. And the way to figure out whether or not we're scaling the first term by plus or minus 1 is to look at the entry, or the location of the entry. -15 is in the 1, 3 position of this matrix. So we want to multiply -15 by -1 raised to the 1 plus 3, which is -1 to the 4, which is plus 1. So -15 is scaled by plus 1, which means that the next term will be scaled by -1, and then the next term, -4, is scaled by plus 1. Now we can focus on the minors that we're multiplying each one of these terms by. For our first term, -15 is in the 1, 3 position, so we delete row 1, column 3, and multiply by the determinant of whatever's left over. Our -66 is in the 2, 3 position, so we delete row 2, column 3, and take a determinant of whatever's left over. And our -4 is in the 3, 3 position. So here we delete row 3, column 3, and take a determinant of whatever's left over. So now, if we were to calculate each one of these 3 terms and add everything up, we would also get the determinant of the original matrix. So in this example, what we have are 2 different ways to calculate the determinant of the original matrix. And if we look at these 2 methods, I think it's clear that one is more attractive than the other. If we look at the scalars we're using in the second row calculation, the middle one is equal to 0, which means that this determinant in the second position is actually irrelevant as far as the calculation is concerned. So that cuts the work back. Instead of actually needing 3 terms for this first formula, we only need the first and third. Whereas in the second calculation here, none of our scalars is equal to 0, so we actually have to calculate each one of these 3 terms to figure out the determinant of our original matrix. So I think the first method is slightly easier than the second method here. So this is exactly why the theorem is so powerful. If our matrix has lots of zeros inside of it, then our strategy should be to choose a row or a column that has as many zeros as possible, because that reduces the work in calculating our determinant. So let's say we were working with the 4x4 determinant right here. If we were working from scratch, we would have to write down 4 terms, and each of those terms would involve a 3x3 determinant, and that would be a lot of work. But since we're working with this 4x4 and we have freedom to choose any row or any column to work with, one thing to note is that there are some zeros in this 4x4 determinant, and there are actually 3 zeros in the third column. So I think it's to our advantage to choose the third column to expand about here. How would this work? Well, we won't need 4 terms, we'll only need 1, which will be scaled by -2. So here, we pluck out the -2, and remember, according to the cofactor formula, we need to weigh -2 by plus or minus 1. Well, -2 in our matrix is in the 3, 3 position, and -1 to the 3 plus 3 is -1 to the 6, which is plus 1. So we're scaling -2 by plus 1. And then we delete the third row and third column of our original matrix and take a determinant of whatever's left over. So now, in one step, we've reduced our 4x4 determinant to a 3x3 determinant. So now we have a new determinant problem on our hands. So now we're working with a 3x3 determinant, not a 4x4. So how are we going to work with this 3x3? Well, again, we could work from scratch and look at 3 terms, each of which involve a 2x2 determinant. But since the cofactor expansion theorem gives us freedom to choose any row or any column to work with, I think it's best if we choose the third column of this new 3x3 matrix, because the third column has 2 zeros inside of it. So if we choose that third column to expand about, the formula says we should pluck out the 7, and we need to figure out if we're multiplying 7 by plus or minus 1, Well, 7 in this 3 by 3 determinant is in the 1, 3 position, and negative 1 to the 1 plus 3 is negative 1 to the 4, which is plus 1. So we're scaling 7 by plus 1. Then we delete the first row and third column of our 3 by 3 matrix and take a determinant of whatever's left over. So now, in our second step here, we've reduced our 4 by 4 determinant to just one 2 by 2 determinant, and 2 by 2 determinants are pretty easy. So now, our 2 by 2 determinant we're taking will be 3 times 4 minus 6 times 1. So when all said and done, our determinant takes the form negative 2 times 7 times 3 times 4 minus 6 times 1. And when we do the multiplication in this example, we end up with negative 84. So this is great because if we were to try to work on this problem from scratch, it would take quite a long time because there would be lots and lots of determinants to take. But the cofactor expansion theorem says we could take advantage of where we have zeros inside of our matrix and reduce the burden of the calculation. Okay, so now I'd like to talk about some further properties of determinants that make calculations even more easy sometimes, or even easier sometimes. So if we think about how the cofactor expansion theorem works, what it's saying is that it doesn't matter if we choose rows to expand about or columns to expand about, we always get the same result when we calculate our determinant. Well, remember that the rows of our original matrix are the columns of its transpose. And since it doesn't matter if we choose rows or columns to expand about, this tells us that the determinant of the transpose of any matrix is always the same as the determinant of the original matrix. So determinants are insensitive to transposition, is what this is saying. So here we have a horrible example. Here we want to calculate a 6 by 6 determinant. Well, one thing to notice about this theorem is telling us that this 6 by 6 determinant is the same as this 6 by 6 determinant. And we'll notice that these two matrices are related by transposes. So this theorem is automatically telling us that at least we know these two determinants are the same, even if it is quite a large determinant to take. And in fact, for this particular example, we can compute this determinant quite fast. One thing to notice about the original determinant is that the fourth column is all zeros, which means that the fourth row of its transpose is all zeros. So if we chose that column in the first matrix or that row in the second matrix to expand about, we would be guaranteed to get the number 0 here. So punchline is determinant of the transpose is always equal to the determinant of the original matrix. Another consequence of the cofactor expansion theorem says that the determinant of any triangular matrix is simply the product of the diagonal entries. Let's illustrate this theorem with an example. So here we have a 4 by 4 determinant to calculate, and this 4 by 4 matrix is not any old matrix. This is an upper triangular matrix. Every entry below the diagonal is equal to 0. So let's say we were doing this determinant. Well, one thing we could do is we could do a column 1 expansion, because in column 1, we have 3 zeros and 1 2. So how would this work? Well, we would simply pluck out the number 2, and 2 is in the 1 1 position, so its cofactor should be weighed positively. So we pluck out the 2, and then we delete row 1, column 1, and multiply by a determinant of what's left over. So now in this new 3 by 3 determinant, we could choose column 1 again because there are 2 zeros and 1 non-zero entry. To do this, we pluck out negative 1, and negative 1 is scaled positively because it's in the 1 1 position of this determinant. And then we delete row 1, column 1 here and end up with a 2 by 2 determinant. And to calculate this 2 by 2 determinant, we can simply use the formula product of the diagonal minus the product of the other two entries. But the 0 in the 2 1 position here says that the product of the other two entries is simply equal to 0. So when we end up calculating our determinant to the end, we end up with the product 2 times negative 1 times 10 times negative 9/5. And we'll notice that each of these 4 numbers are exactly the 4 numbers on the diagonal of our 4 by 4 upper triangular matrix. When we multiply those numbers together, we end up with 36 here. So once we notice this pattern of applying the cofactor expansion theorem repeatedly to the first column of an upper triangular matrix, we realized that we'll always just get the product of the diagonal entries. So we could have just stared at the original matrix and said, this is upper triangular, so all we need to do to calculate the determinant is multiply these diagonal entries together, and we get a quick determinant calculation. Another consequence of this is we can immediately calculate the determinant of any identity matrix. The identity matrix is certainly both upper triangular and lower triangular, and its only diagonal entry is equal to 1. So to calculate the determinant of the identity matrix, we just multiply 1 by 1 by 1 n times, and of course that product is equal to 1. So the determinant of an identity matrix is always equal to 1. Our next property of determinants says that determinants actually play very nicely with products. If we wish to calculate the determinant of the product of two square matrices, it turns out that this is always the product of the two individual determinants. So while determinants are insensitive to transposition, determinants are sensitive to matrix multiplication. To calculate the determinant of the product, we could instead calculate the product of the two determinants. So imagine a situation where we end up with something like this. Here what we have is a matrix factorization. This matrix on the left is a complicated 4x4 matrix. But we've managed to somehow factor this 4x4 matrix as the product of two other 4x4 matrices. And the thing to notice here is that the two matrices that we're multiplying together are both triangular matrices. This first matrix is an upper triangular, and the second matrix is a lower triangular. So we can quickly calculate the determinant of this matrix on the left, or this upper triangular matrix. Since this matrix is upper triangular, all we need to do is multiply the diagonal entries here. The determinant should be 1 times -3 times 2 times 1, which of course has product equal to -6. Our determinant calculation for this matrix on the far right is equally similar. This is a lower triangular matrix, which means its determinant is the product of the diagonal entries. So here to calculate the determinant, we should multiply -1 times -1 times 2 times 1. Well, -1 times -1 is 1, 2 times 1 is 2, so we end up with the determinant equaling 2. So now that we know that our original complicated 4x4 is the product of two matrices where the first matrix has determinant -6, and the second determinant has the second matrix has determinant equal to 2, all we need to do to calculate the determinant of our matrix on the left is multiply -6 by 2, which tells us that the determinant that we're seeking is actually -6 times 2, which is equal to -12. So once we have our factorization, we don't have to work very hard in this example to calculate our complicated determinant. Okay, so a lot of this will come together to end up saying that some of the work we've been doing, or that we've done previously, helps in our quest to calculate determinants. If we think of like our LU factorization, if we manage to factor a matrix as L times U, that means that our matrix is the product of a lower and upper triangular matrix, and those two triangular matrices have determinants that are easy to calculate. Well, fortunately for us, when our algorithm for calculating a PA equals LU factorization involves elementary row operations, and elementary row operations play nicely with determinants. So remember, there are three types of elementary row operations. There's row switching, there's row scaling, and there's row addition. Our first theorem here says the following. If we start with a matrix A and perform a row swap to obtain a matrix B, it turns out that the determinant of the new matrix, B, is guaranteed to equal the negative of the determinant of the original matrix A. So effectively what this theorem says is that if we switch two rows of a matrix, that negates the determinant of that matrix. Our second theorem says, let's say we start with a matrix A, and we scale one row of that matrix by a number C to obtain a matrix B. In this situation, the determinant of the new matrix is related to the determinant of the old matrix. The determinant of the new matrix B turns out to always equal the number C we used to scale our row multiplied by the determinant of the original matrix. So row scaling results in scaling determinants. And finally, the most important of these three properties involves row addition. Let's say that we start with a matrix A and do row addition to obtain a new matrix B. It turns out that it doesn't matter what row addition we performed, the determinant of the new matrix is always the same as the determinant of the original matrix. And this is fantastic for us because if we think about the operations we use to calculate an LU factorization, we only use row swaps and row addition. Whenever we do a row swap, the worst we're doing to a matrix is we're negating the determinant. And whenever we do row addition, we're not changing the determinant at all. So that suggests a strategy. These theorems are suggesting that we can simplify our determinant problems by row reducing our matrix to a simpler matrix B. And when we say simpler, what we mean is a matrix that has lots of conveniently placed zeros. Okay, so let's do a 4x4 determinant using this method. So here we have the task of calculating this 4x4 determinant. And one of the issues here is that this matrix doesn't have any zeros inside of it. So despite the cofactor expansion theorem being an option here, there's no row or column that is particularly advantageous to choose because there are no zeros here. So instead of using the cofactor expansion theorem, let's use the idea of row reductions. Let's start with this 4x4 and focus on the upper left-hand corner where we have a 1. Let's use that 1 to clear out all of the entries below the 1, 1 position. So the operations for doing this are to take row 2 and subtract row 1. Then we take row 3 and add row 1. Then we take row 4 and subtract row 1. And according to our theorems from the previous slide, since each one of these operations is row addition, we're actually not changing the determinant at all when we do these operations. So this is great for us because this takes our complicated 4x4 and it turns it into an easier 4x4 where we have more zeros here. Cool. So we're not done row reducing though, because I'm not going to be happy until the matrix that we're focusing on is a triangular matrix and I can just easily take the determinant. So I'm done clearing out the entries in the first column. Now I want to move to the second column. So now I move right 1 and down 1 where I have a 4. And let's see if we can take that 4 and clear out all of the entries below it. Well, the entry immediately below our 4 is already equal to 0, so I don't have to worry about the third row here. But the fourth row is equal to 3. So my next operation will be to take row 4 and subtract 3/4 row 2 from it to clear out the 3 in the 4, 2 position. So after doing that operation, we've made our matrix even nicer. And again, we haven't changed our determinant at all because we're only using row addition in this step. So now we've cleared out all of the entries below our pivot in the second column. Again, though, I'm not upper triangular yet, so I'm going to keep going. I'm going to move right 1 and down 1 and ask myself whether or not I can use this position as a pivot. Now here, we have a 0, which cannot be a pivot, so we need to swap with a row below it. And we can swap with row 3 with row 4 to get a pivot. So if we now swap row 3 with row 4, we now have produced a matrix that's upper triangular. But remember that row swaps negate determinants. So all 3 of these first 4x4s have the same determinant. But once we swap row 3 with row 4, we negate our determinant. But this is great because now we know we just need to tack a -1 onto our calculation and we'll get our answer. And the beauty of the theory now says, well, we've successfully row reduced our matrix into upper triangular form, and upper triangular matrices are easy to take determinants of. All we need to do is multiply all 4 of the diagonal entries here. So now we know that our answer should be -1 to account for the negative we got in our determinant calculation by switching 1 row. And then we should multiply 1 times 4 times -21 times -2. When we multiply all of those together, we end up with -42. So we've successfully calculated a 4x4 determinant here by only doing elementary row operations. Effectively, what we've done is we've used the LU algorithm and we've started with a matrix and row reduced it to an upper triangular form. Since we only used row addition, where the determinant doesn't change, and row swaps, where the determinant only changes by a factor of 1, the only thing we need to do is keep track of the number of row swaps and then multiply by the pivots that we get at the end of our calculation. Since the PA equals LU algorithm works exactly in this way, we should end up with a quick way to find the determinant of our original matrix once we have the PA equals LU factorization. Let's see this in an example. So here what we have is a PA equals LU factorization that we calculated previously. So here the matrix P multiplies by A to equal L times U. Now, remember that determinants respect matrix multiplication. So if we could individually find maybe 3 of the 4 determinants of these matrices, we can find the missing determinant. And of the 4 of these matrices, I think by far A is clearly the hardest determinant to calculate. So let's look at the determinant of maybe L here. Well, L is a lower triangular matrix, and all of the diagonal entries are equal to 1. So we immediately know that the determinant of L is equal to 1. What about the determinant of U here? Well, U is an upper triangular matrix, so all we need to do to calculate its determinant is multiply the diagonal entries together. So here the determinant of U should be 3 times 5/3, which is 5. Then we multiply by 9/5, which is 9. So the determinant of U here is equal to 9. Let's go back to the left-hand side of this equality and look at the matrix P. Remember that P in our algorithm is obtained by just doing a bunch of row swaps on the identity matrix. And since the identity matrix starts with determinant 1, every time we do a row swap, we end up just negating the number 1. And if we look at this matrix P, what we see is that P was obtained by only doing one row swap. If we switch row 1 with row 3 here, we're back to the identity. So we immediately know here that the determinant of P is equal to -1. So now when we put all this information together, we know that -1 times the determinant of A should be equal to 1 multiplied by 9. And when we put all that together, what that's telling us is that the determinant of A is equal to -9. So the big idea here says this example actually generalizes. So if we pay attention to the mechanics here, if we think about how L is constructed in PA equals LU, L is always a lower triangular matrix that has 1 on the diagonal. So the determinant of L will always be equal to 1. U is always an upper triangular matrix, and the entries on the diagonal of U do not have to equal 1. So there are, in general, some interesting numbers on the diagonal of U. Also, the matrix P is obtained by doing row swaps on the identity matrix. So the determinant of P is going to be plus or minus 1, where whether or not we choose plus or minus 1 is determined by the number of row swaps we do in our algorithm. So this gives us a nice way to calculate the determinant of a matrix by using the PA equals LU algorithm. So let's say that we know that P times A equals L times U. Well, we quickly get a formula for the determinant, which says that the determinant of A is always equal to -1 raised to the number of row swaps it took to get from A to U, multiplied by the determinant of U. And the determinant of U is always easy to calculate because it's an upper triangular matrix, so we only need to multiply the diagonal entries together to obtain that determinant.